day, everyone. My name is Leonard Brown, and this is my lecture on recursion from a series of lectures I've developed to teach Excel Lambda fundamentals. Your feedback would be appreciated. The standard definition of recursion is a function that calls itself. This definition is correct, but in my opinion, not intuitive. I believe a more intuitive definition is a program that solves a problem by creating new instances of itself to solve smaller versions of the original problem. Eventually, it will reach a base case which does not require further recursion, and a cascade of returns will occur. Now, let's use a regular programming language to write a recursive function to calculate the sum of numbers from 1 to n. Let's name this function sumn. So sum n of 100 is equal to 100 plus sum n of 99. Sum n of 99 is equal to 99 plus sum n of 98. So we can generalize and write sum n of n is equal to n plus sum n of n minus 1. And we also know that sum n of 1 is equal to 1. As you can see, the recursive program to solve this problem only contains two pieces of information. The fact that sum n of 1 is equal to 1, and the fact that sum n of n is equal to n plus sum n of n minus 1. On each subsequent call to sum n is being called with a smaller number till we get to 1, at which point we know sum n of 1 is 1, and we get a cascade of returns till we get back to the original call. Note that sum n is being used as part of the definition of sum n. So sum n is being used before it is fully defined, right? This is not allowed in Excel Lambda or Lambda Calculus, upon which Excel Lambda is based. In Lambda Calculus, you cannot use a name before it is defined. Obviously, we could also have solved this problem using iteration. Iteration typically involves the modification of variables, as shown here. Lambda Calculus, and by extension, Excel Lambda, does not allow you to modify or mutate variables once set. So Excel Lambda does not have traditional iteration. Excel Lambda does allow recursive calls. However, there are restrictions on how these recursive calls are defined. For many problems that typically require repetition, if the number of repetitions are known, there are typically simple non-recursive solutions. For example, here are two lambdas that solve the factorial problem without recursion. The first simply uses the built-in factorial function. The second uses a combination of Excel's product function and sequence function to solve this problem. Excel also has a reduce function that can be used to solve problems requiring repetition without explicit recursion. This is demonstrated here. Again, if you know the number of repetitions, there are most times non-recursive solutions to problems requiring looping. The recursive solution to the factorial problem is very elegant. It uses the two simple properties of the factorial. The fact that factorial of n is equal to n times the factorial of n minus 1, and the fact that the factorial of 0 is 1. By the way, if you're unaware that the factorial of 0 is 1, I would suggest you explore this answer on Google. Here we've written a recursive lambda to calculate the factorial. Microsoft indicates that recursive Excel Lambda functions need to be defined using an external naming mechanism prior to being used. So, For this recursive lambda to work, we have to name this function lbfact in an external name manager, in Excel, or in Google Sheets. Now we'll assume that lbfact has been named externally so that we have a valid recursive lambda. Let's see what happens when we calculate lbfact of 3. When we call lbfact of 3, n is not equal to 0, so this function resolves to 3 times lbfact of 2. So it makes a call to lbfact of 2. When we call lbfact of 2, this resolves to 2 times lbfact of 1. When we call lbfact of 1, this resolves to 1 times lbfact of 0. Now when n equals 0, it returns 1. So we know that lbfact of 0 is 1. So this function returns 1. So now we know lbfact of 0 from returning from the previous call. So lbfact of 1 is 1 times 1, which is 1. So we know lbfact of 1 is 1. Now lbfact of 2 is 2 times lbfact of 1, right? So lbfact of 2 is 2 times 1, which is 2. Now we get back up to the original call, lbfact of 3, which is lbfact of 3 is equal to 3 times 2, because we know it from here, and that's 3 times 2 is 6. So that is what that is saying is that the factorial of 3 is 6, and we know that to be correct because we know that the factorial of 3 is 3 times 2 times 1, which is 6. So as you can see, each of these are independent calls, just as this might have called a different function. It happens to be calling itself, and it calls it multiple times till it gets to a base case, and then each of those return to give you the answer. That's effectively how a recursive function works. It is possible to create a recursive function in Excel Lambda without using external naming. The top lambda shown here is invalid because the name fact is being used before it is defined. This is not allowed by lambda calculus upon which Excel Lambda is based. However, as shown in the second lambda, we can get around this problem by including a parameter as a placeholder for the recursive calling function's name. We then use the placeholder parameter to make the recursive calls. By using the placeholder, we do not violate the naming rules of lambda calculus, and the lambda is valid. Note, we now need to include the recursive calling function's name in the parameter list, so our recursive function will now have 2 parameters instead of 1. The placeholder function must have the same parameters as the original recursive function. So it too will have 2 parameters. At execution time, by including the calling function's name in the parameter list, we are effectively assigning the placeholder to the calling function's name. In so doing, we get a fully recursive function. I thought it would be great to write a lambda to convert an improper fraction into a mixed fraction using subtraction only. An improper fraction is one where the numerator is greater than the denominator. A mixed fraction is a whole number plus a regular fraction where the numerator is less than the denominator. Division can be considered to be multiple subtractions. We will constrain the problem so we cannot use multiplication or division, only subtraction and addition. To solve this problem, we will need the number of times you can subtract the denominator from the numerator, and we call this the whole part. So it's how many times, say, you can subtract 10 how many whole times you can subtract 10 from 39, which would be 3, and the remainder after subtracting a whole number of denominators. So for example, for the improper fraction 39 over 10, the remainder part would be 9. Knowing 1 determines 2 and vice versa. However, for demonstration purposes and given the no multiplications constraint, we will calculate 1 and 2 independently using recursion. Here we have developed a recursive lambda to calculate the whole number of times you can subtract the denominator from the numerator. You'll notice I'm using the placeholder variable f underscore ll. When the recursive function is called, here whole part ll, I'm including the whole part as a parameter so that we set the placeholder equal to the value of the recursive function's name such that this function becomes recursive. Now let's examine what happens when this lambda is executed. Obviously, the arguments are 39 and 10, so iNumerator gets set to 39 and iDivisor gets set to 10. Whole part gets called with the numerator of 39 and the placeholder name gets set to whole part such that this function becomes recursive. Now, when we call it, the first thing we call it with is whole part of 39, which is here, right? So if it gets called with 39, 39 is not less than divisor, right? So it calls itself again with 39 minus 10, which is 29, right? So whole part of 39 is equal to whole part, because this is a placeholder for whole part of 29 plus 1, which is what we see here. So it makes a second call to whole part with 29. Whole part of 29 is whole part of 19. Again, we subtract 10 plus 1. Whole part of 19 is equal to whole part of 9 plus 1. Whole part of 9 is less than divisor of 10, so it returns 0. So we know whole part of 9, right, is 0, right? So whole part of 19 is whole part of 9, which we just calculated as 0, plus 1, which is 1. Whole part of 29 is whole part of 19, which we just calculated here, which is 1. 1 plus 1 is 2. Whole part of 39 equals whole part of 29, which we just calculated as 2, plus 1 equals 3. So we get whole part of 39 equals 3. Again, this is how the recursive function works in calculating the whole part. Now let's look at the lambda to calculate the remainder part. You can see this lambda here. And the key thing is, it says if the numerator is less than the divisor, we return the numerator. If the numerator is not less than the divisor, we return the iterative function remainder part as the numerator minus the divisor. So let's walk through and see how it works when we execute this function with the arguments 39 over 10. Right? So numerator is 39, divisor is 10. So let's look. Remainder part of 39 is the numerator is greater than the denominator. So we just subtract by 10. We call the remainder part with the numerator minus 10, which is 29. Remainder part of 29, the numerator is still greater than the denominator, so we call this with remainder part of 29 minus 10, which is 19. Remainder part of 19 is still greater than the denominator 10, so we call it the remainder part of 19 minus 10, which is 9. Now at this point, the numerator is less than the denominator, so we return the numerator, which is 9. So the base case returns 9. So now that we have here remainder part 19 is remainder part of 9, so this returns 9. Remainder part of 29 is remainder part of 19, which we know is 9. This returns 9. Remainder part of 39 is the same as remainder part of 29, so this returns 9. So 9 just bubbles all the way up, and we get a remainder part of 9, which we know to be correct. So we're finally in a position to create a lambda to convert improper fractions into mixed fractions. And this will walk through the lambda. This is the lambda here, and I'll walk through how it works. It takes two arguments, the numerator and the denominator. The parameters I have here are I numerator and I divisor. So the first thing I do is check to see if the divisor is equal to 0. If the divisor is equal to 0, it returns an error message, error divisor is 0, and the lambda exits and returns. Otherwise, it does the let section. And the first assignment, the first variable assignment of the let is a comment. I'm using label underscore 100, which is a valid label in Lambda, in Excel Lambda, as well as Google Lambda. And I have a string, and the string just tells you what this function does. This is a wise thing to do, so if somebody looks at a function, they know exactly what it does, right? And here I have the whole part recursive function, which I discussed previously, and I have the remainder part recursive function, which I discussed previously. And then what I do is I'm going to create a string via concatenating a bunch of variables together to create this this string. So what I do is I numerator, which is a numerator concatenated with a slash divisor, which is this part of the string, concatenated with equal, and then I have the whole part function, which I call, and if you notice, whole part is a parameter to this function. So I get the recursive part with the I numerator as the parameter, right? And that whole part returns 10, which is this. I concatenate it with plus, and then I calculate the remainder part. Again, the remainder part has a parameter. Along with I numerator, and that returns 9, and then I concatenate it with slash divisor, and I get, it's a relatively simple function, but it actually is using two recursive functions to calculate the whole part and the remainder part, and I think it's actually quite elegant. If you notice, I just have one for my return function. I just have result of the let, and that returns, and this works fairly well. It's not an overly complicated function. I would strongly suggest that you copy this function into Excel and test it out for yourself. But this is I think, a very good example of the use of recursive functions. Well, I think we have done a fair job covering Excel Lambda Recursion. I do hope you found the material useful. This is my first YouTube video. I would really appreciate if you could provide some feedback, positive or negative, in the comments below to guide me in developing future videos. Thanks for watching. Have a nice day.